relevance of problem. The problem connects to Avogadros number because it uses the same process of turning grams into moles and then into actual particles. Avogadros number lets us count molecules through math and by converting grams of CO2 into moles and then molecules. The problem shows why the number is so important. A sample contains 4.75 grams of carbon dioxide. Using Avogadros number, how many carbon dioxide molecules are in the sample? Question, how many CO2 molecules are in 4.75 grams of CO2? Benefits of problem. Understanding this problem shows how Avogadros number is actually used in chemistry. Instead of just memorizing the number, you can convert grams to moles and then to molecules. This makes the mole feel more real because you see how it applies to actual sample of CO2. Skills gain. By solving this problem, a person learns how to convert grams to moles, use molar mass, apply Avogadros number to find particles, set up a multi-step chemistry calculation. Other problems they could solve. After this, someone could move on to finding particles from any mass, converting particles back to grams, doing mole ratio problems, and calculating product amounts in chemical reactions. Development of problem. I made this problem from scratch by choosing a real substance and a realistic mass that could be converted with Avogadros number. I used carbon dioxide and 4.75 grams because it is a normal lab amount and lets you do the full gram to mole to molecule conversion. It's not too simple because it is a multi-step problem. You first find moles using the molar mass of CO2, then use Avogadros number to find the molecules. You cannot guess the answer and it requires real math. It's not too difficult because it only uses skills already covered in class. The numbers are easy to handle and you work with one substance, so there is no balancing or complicated steps. It was challenging to make a new problem that still fit with Avogadros number. I had to choose a mass that was realistic, avoid answers that were too extreme, and make sure the problem was more than a simple definition while still being easy enough to solve. Uniqueness of problem. Most Avogadros number problems only use one step, like turning moles into particles. My problem is different because it starts with the real mass of CO2 and makes you convert grams to moles and then molecules. It uses real amounts and full multi-step process, which makes it more meaningful. This problem goes further by taking you through the whole conversion path. It starts with grams, then moles, then molecules, showing why Avogadros number matters when counting particles. It also builds skills needed for harder chemistry topics. To make it unique, I added a realistic mass of CO2, the need to use molar mass, the full mole conversion process, and the final step of finding the total number of molecules. The graph shown below shows how the number of CO2 molecules increases as the mass increases. Each point is a real conversion using moles, and the pattern shows that more mass always means more molecules. 1 gram of CO2 shows that even tiny masses contain huge numbers of molecules. 2 grams doubles the molecules. 3 grams continues the same pattern. 4.75 grams of CO2 matches the unique problem and shows exactly where it falls on the graph. 6 grams is a larger sample that still follows the same relationship. All points show that molecules increase in direct proportion to mass. The graph is linear. As mass increases, the number of molecules increases at the constant rate. grams to moles is linear, and moles to molecules is also linear. So the pattern matches what Avogadro number predicts. Formulas for the problem. Moles from mass, N equals mass divided by molar mass. Particles from moles, N equals N times Avogadro's number. Constants, Avogadro's number 6.022 times 10 to the 23rd particles per mole. Molar mass of CO2 about 44.01 grams per mole. Units used gram for the mass of CO2, grams per mole for the molar mass, mole for the amount of substance, molecules or particles for the final count of CO2, particles per mole for Avogadro's number. Solution for the problem. The mass of carbon dioxide sample is 4.75 grams. The molar mass of carbon dioxide is 44.01 grams per mole. Avogadro's number is 6.022 times 10 to the 23rd particle per mole. The goal is to find how many carbon dioxide molecules are in the sample. Step 1 is converting grams to moles. Using the formula N equals mass divided by molar mass, 4.75 grams divided by 44.01 grams per mole gives about 0.108 moles of carbon dioxide. Step 2 is converting moles to molecules. Using N equals N times Avogadro's number, 0.108 moles times 6.022 times 10 to the 23rd gives about 6.50 times 10 to the 22nd molecules. The final answer is that 4.75 grams of carbon dioxide contains about 6.50 times 10 to the 22nd molecules. Verification for the problem. First, I turned 4.75 grams of carbon dioxide into moles by dividing by the molar mass. That gave about 0.108 moles. Then I multiplied that by Avogadro's number, which gave about 6.50 times 10 to the 22nd molecules. Repeating these steps gives the same result, so the math is consistent. To see if the answer is reasonable, 1 full mole has 6.022 times 10 to the 23rd molecules. My sample is about 1/10 of a mole, so I should get around 1/10 of that amount. My answer, 6.50 times 10 to the 22nd, fits that range. The units also checked out. Grams divided by grams per mole gives moles in the first step, and moles times particles per mole gives molecules in the second step. That means the formulas were used correctly. Checking the size and the unit shows that Avogadro's number is being applied the right way. It proves that the gram to mole to molecule steps we talked about actually work with real numbers, just like chemists use in real samples.
Today we'll be talking about Avogadro's number. We'll first start off with the uniqueness of problem. When I created my brand new Avogadro's number problem, I wanted it to look noticeably different from the typical examples I usually see in textbooks or online. My problem was a sealed container holds 0.25 grams of helium gases at STP. Using Avogadro's number, how many helium atoms are present, even though it uses familiar chemistry concept. The way I designed it makes it more meaningful and more realistic than the standard problems. I chose helium in purpose because helium is monatomic. The number of particles equals the number of atoms, which avoids confusion and reinforces correct atomic thinking. Question. A sealed container holds 0.25 grams of helium gas at standard temperature and pressure. Using Avogadros number, how many helium atoms are present? Answer. Na equals 6.022 times 10 to the 23rd power particles. This problem goes further by making the students calculate the total mass from individual atomic masses. This reinforces that Avogadros number is abstract. It has measurable consequences. This problem extends that by adding a step where the student verifies the mass, again using microscopic data. The development of problem. Helium is commonly used in balloons in science labs, making it recognizable. A tiny sample of helium connects everyday experiences to microscopic atomic behavior. Benefits of problem. The problem shows how a very small mass of helium gas contains an enormous number of atoms. By converting grams to moles to atoms, students learn how chemists link what we can measure in the lab to the invisible particles that make up all matter. Visual for problem. 0.1 gram sample shows that even tiny samples contain tens of sextillions of atoms, emphasizes the microscopic scale. Formula for the problem. Moles from mass, number of atoms from moles, scientific notation, A times 10N. Solution for problem. Step 1, identified known values and what was being asked. Step 2, converted mass to moles. Step 3, converted moles to atoms using Avogadros number. Step 4, confirm units and scientific notation. Verification for problem. Problem recap. A sealed container holds 0.25 grams of helium gas at STP. Using Avogadros number, how many helium atoms are present? Step 1. Check the calculation for reasonableness. Verify moles. Step 2. Check the solution against possible ranges. Step 3. Check units. Mass in grams. Moles are in mol. Number of atoms is in atoms. And that is it for today.
So I'm going to be recording part D of my Avogadros number project for physics. So for the first slide, we have relevance of problem. My new problem relates to Avogadros number because it uses the same idea we learned in earlier parts of the project, counting numbers of particles in a substance before we worked on examples, showing how 1 mole has 6.022 times 10 raised by 23 particles. My problem is similar, but it uses different number of moles. This makes it a new situation that still follows the main concept. This problem requires real numerical solvings because you have to multiply the number of moles by Avogadros number to find the total of numbers of a molecule. It is not fill in the blank or multiple choice question. You need to do actual math steps, which helps understand the topic better. So we have, benefits of the problem. Understanding this problem is helpful because it shows how to use Avogadros number to find the number of particles in a substance. It makes the idea of moles and numbers easier to understand. By solving this problem, a person practices multiplying large numbers using powers of 10 and applying formulas step by step. After solving this problem, a person could solve other problems like finding the number of atoms in a compound, the number of molecules in a gas, or calculating the numbers of particles in different amounts of substance. For the third step, we have development of problems. I made my problems from scratch by choosing the number of moles, 2 moles, and asking how many molecules are in that amount. Then I used Avogadros' number to turn it into a real math problem. This problem is not too simple because you have to use the formula by multiplying it by a very large number. You also need to handle the powers of 10 correctly. This math problem is not too hard because the steps are clear and only one formula is used. The numbers are easy to work with. It was a little difficult to write the problem because I had to make sure it was new and not the same as the textbooks or online. I also avoided making a multiple choice or just a definition question. Got that. I needed real calculations to solve this. So the uniqueness of the problem, this problem is different from textbooks or internet problems because I picked my own numbers of moles instead of the usual 1 mole example. It is new and not copied. Most common problems are very simple and use the same examples. My problem uses different numbers and asks for a total number of molecules, which makes it unique. I added my own numbers to make sure you have to do real calculations. This makes it more original and useful to practice. This problem goes beyond common examples because it helps students practice multiplying by Avogadros' number in a new way. Formula for my problem. Main formula: n equals n times Na. Variables: n equals number of particles, which is atoms or molecules. The smaller n equals number of moles. The constant, I don't really know how to read that, but there it is. Units: smaller n in moles, and big N is number of particles, Na in particles per mole. Here is my visual for the problems for slide 4. And you can see I made a table to show the number of molecules changes with different numbers of moles. An explanation of the data: when the number of moles increases, the number of molecule also increases. The relationship is linear because doubling the moles doubles the number of molecules. Each point shows how the same formula works with different amounts of substances. Yes. Here is the solution for my problem. Problem is 2 moles of water. Find the number of molecules. So you can see right here. Alright, so the formula. Here's the formula. I don't know if you can see that. Alright, so step 1, write the known values, which is n equals 2 moles. Step 2, multiply. You can see that. And step 3 is answer. They're about 1.20 times 20 to the 24. Verification for my problem. We check the calculations. Just close up. Okay. The math is correct, hopefully. The answer is reasonable. 1 mole has 6.022 times, let's see. Okay, 10 to 23 particles. 2 moles should have about twice that, which is, there's the number. Units are correct. Number of particles. The problem is useful because it shows Avogadros' number links moles to the actual number of particles. Today I will be talking about Newton's universal law of gravitation, part D. So I have relevance of the problem. My new problem relates to Newton's law of gravitation because it uses the same gravity formula we learned earlier in the project before we worked on examples that showed how gravity depends on mass of 2 objects and distance itself between them. The new problem follows the same idea, but with the different numbers and different objects. This problem fits the topic because it uses the main gravity equation to find force you have to put in real numbers and solve the answer. It is not fill in the blank multiple choice question. It is real math steps and it connects what we learned and shows how the law of gravitation works in new situations. Second part, we have benefits of problems. His problems is useful because it helps someone to see how gravity formula works with real numbers. It makes the idea of gravity easier to understand. By solving it, a person practices using a formula, plugging in numbers, and doing simple math. After doing this problem, they can solve other gravity problems like finding force between objects and different distances. The development of my problem. I made my problem by choosing 2 objects giving them masses and picking distance. The problem is not too simple because you have to use the formula to solve the force. The problem is not too hard because the numbers are and steps are clear. And it was a little, did I not fucking read this? Man, fuck, dude. The uniqueness of my problem is different from common textbooks or internet problems because I choose my own numbers for the masses and the distance, and it is not copied from any source. Most common problems have large objects like planets. My problem uses two small spheres, making it different. It also picks numbers that are not usually used in examples. I added my own values to set up the distance myself. This problem is new and not found online. I hope so. My problem goes above common problems because it is fully original, but it still uses gravity formula. It lets someone practice real math while working numbers that they do not normally see in basic examples. For the visual of the problem, I made a table that shows the gravitational forces. One changes the distance between two objects and changes. Explanation of the data: when the distance gets bigger, the forces get smaller. The relationship is inverse square because force decreases with the square of the distance. Each point shows the same two objects interact differently at different distances. Next, I have the formula for my problem. See the main formula? That would be this one right here. The variables is F equals gravitational force. The units is N. M1 equals mass of the first object. M2 mass of the second object, and R distance between objects. The constant is -g equals 6.67 times 10 to the negative 11. All right. Here are the solutions for my problems. Step 1, write down the values. All right. Step 2, write down the values. And then for step 4, square the distance. In step 5, you would divide by R to the second power. And step 6, write the final answer. And my explanation for this: multiply masses to bigger objects have more force. Multiply by G makes the force correct for real units. The square distance, gravity, gets weaker with more distance. Divide by R2, it's the final force, and the answer in units, the unit for force. And verification for my problem: check the calculation. Here's my calculations. And the math step is correct. Check the value if the value is reasonable. And the third step would check the ranges of possible answers, and the fourth would be value to the project topic. That would be all for my part of this project.